Okay, guys, we're back. So, here's the thing. We did it. We created our table with friction, or I'm sorry, without friction. And now we're going to do it with, okay? So, here we are doing it with friction. And I'm going to do just a little bit of an example. We're going to look at point 4. And I'm going to slide over here to the side. So we can look at point 4. And we want to know what the work of friction is at point 4. So work of friction, that's going to be equal to our force of friction times our distance. And the distance at point 4 is 50 meters. Let's stick some meters on there. Excuse me. And we've been given right here the force of friction is 125 newtons. So we're going to do 125 newtons. We're going to multiply that by our 50 meters. And that's going to give us something. I'm sure I have it written down somewhere, but who cares? 50, 125 times. Okay, 6,250. 6,250 joules, or 6.25 kilojoules. All right. Good. Okay, how does that figure in on our little graph here? How does that figure in? So let's do it. This whole thing is 122.5, and we've only got 6.25 of it missing. So it's really quite a little thing. It's not a huge bit, but that right there is the work lost to friction. Okay, now I chose point 4 for a couple of reasons. One is that the bar is big and has room for me to write to draw in. The other one is all of our energy at that point is kinetic energy. So what does that tell you? It can't cut into our potential energies. It can only cut into our kinetic energies. So our total mechanical energy at that point, because it's all kinetic, ends up being only what's left over our total mechanical energy. So total, oh boy. Okay. Our energy, total mechanical energy, is equal to our kinetic energy at every point along the way, kinetic energy plus our potential energy, and minus our work of friction. Okay? So that's the only thing that we have left over. It can't cut into this one. It can't cut into that because your potential is your potential at wherever you happen to be. So it can only take away from the kinetic energy. That's the only thing that this can possibly take away from. What does that mean? That means that your kinetic energy will go down as a result of friction, and your velocity will go down. Your ability to get more potential energy also goes down. So that's something to think about. If you have enough friction in the system, if there's enough friction, let's say the force of friction is equal to 500. I may do this later. 500 newtons. You might not make it. You might only make it up this high on our roller coaster and then have to go back down. So you wouldn't make it up all the way back up to this 10-meter height. So so we've got some work to do to figure out what the work due to friction is. Okay, we're going to do this equation, force of friction times the distance, and all we have to do is write down what the distances are for the different points, okay? So I've kind of adjusted our table down below. So we've got 20, 26, 50, and 80. Okay, I can remember that, I hope. So 0, 20, 26, 50, and 80. Okay, here's our work of friction right here. We figured out the work of friction at 0.2, 6.25 kilojoules. We can do the same thing. I'm going to just do the work of friction column. And you know what? Our potential energies, I deleted our potential energies, and I probably shouldn't. We have nothing but potential energy at the top. 2.5 K. I don't have that number anymore. I'll get it. Oh, U at 0.2. There it is, right there. So 98K. Uh, 0.349K. 0.5 is 49K. Okay, because those don't change. Those are going to stay the same. All right. So let's do our work. Okay. We've got the work of friction. We've got our 1.25, or I'm sorry, 125 times our distance is 0 here, so we lost nothing. We lost nothing there. We've done 0.4. Let's do 0.2. Along the way, that's 20. So we're going to multiply by 20. And that is 2.5 kilojoules. 125. And we're going to multiply by 26. 3.25. 3.25 and 80 times 125, and that's 10,000. Okay, kilojoules. I've written it in kilojoules up here. Okay, so good. Excellent job by us. Now, so we can't adjust our potential energy, but we can adjust our kinetic energy because it's going to be dropped by whatever this energy is, right? So our kinetic energy is the total. How are we going to do this? we're going to say kinetic energy is equal to, we can slide this up a little bit. Let's not start with what it's equal to. Let's not try and figure out what that is. Let's do this instead. Our total mechanical energy, we know, is equal to our kinetic energy plus our potential energy. We also know that our energy total is going to equal our energy total mechanical minus plus the work that we have done by friction. Because this decreases by friction, this increases by friction, keeping our total energy the same. All right. Let's write E total equals KE plus U plus the work of friction. That means that KE equals our total energy minus our potential energy minus the work of friction. Okay? Do we remember what our total energy was? And I've got a thing here, 122.5 kilojoules. And I've got a column for our energy total. And of course, because of the conservation of energy, this energy total has to be the same all the way down. So let's just fill that in real quick. Okay, that's in kilojoules. So we've got our energy total minus our potential energy, which we've already figured out, minus the work of friction is going to be our kinetic energy. And this is a big one because that kinetic energy is how we're going to get this value for the velocity. I wrote in just so we can compare the velocity without friction, and so we'll see a little difference there. Okay, so that's what we're going to do for all of these kinetic energies. Let's figure them out. So we've got 122.5, and we're going to subtract off 98. And then we're also going to subtract off 2.5. That leaves us with 22. 22K. Same thing goes. 122.5. This time we're going to subtract off 49. 49. That's this. Subtract. And then 3.25. We're going to subtract that, and we're left with 70.25. Okay. 50. Well, 122.5. We're going to subtract off 6.25 because there is no potential energy. So we're just going to have to subtract off, and we're left with 116.25 K. And then we have our last one, and our last one is 122.5 minus 10. 49. We're going to subtract off 49. 63.5. 63.5. kilojoules. Okay. Great. Good job. So our total mechanical energy is this. Okay. So let me reiterate. Total mechanical energy is your kinetic energy plus your potential energy. That's the only mechanical energy that you have. Okay? The total energy includes all of the energy. That's why you have to include the work of friction. Okay? So that's the difference. Total mechanical is only the energy you have available to you to use mechanically. Okay? Mechanical energy is the energy that you have to do work with mechanically. That work of friction was just energy that got thrown out of the system. Okay, so this is a good thing to know. Okay, let's come back down and let's find out what our total mechanical energy is. So we're going to be adding our potential. So for number one, or point one, our potential energy plus our kinetic energy equals our 122.5. So at the very beginning, we have all of our total energy is available for mechanical energy. By the time we get to point two, 98 plus 22 is 120. So we've lost the 2.5 here. 49 plus 70.25, 49 enters 72.5 plus, not 72, 70.25. Add that. 119.25, 119.25. 116.25 is all we have for the third or fourth point. 116.25. And then the last point, we have 49 plus 63.5. 49, 63.5. And that's 112.5. So 112.5. And so what does that do? How can we see that in our slowing down of the cart? Let's do that. We did 1/2 mv squared, right? So let's, oh boy. Let's do our 1/2 mv squared. So our kinetic energy, whatever it happens to be, equals 1/2 mv squared. That's going to give us V equals 2ke on m square root. Okay? So V equals 2ke on m square root, pardon me. So 2ke over m square root. All right. Let's do it. 22,000. Of course, at the very beginning, it's 0, right? Kinetic energy 0, so we got 0, 0, 0. Although everybody's 0. 22,000, I just entered into my computer. I'm going to divide by the 500. And I'm going to multiply by 2. And then I'm going to take the square root. And that gives me 9.38. 9.38 meters per second. So compared, we've kind of dropped off a little bit, right? Friction is slowing us down. Okay. 70.25. 70.250. Enter. We're going to multiply that by 2. We're going to divide by 500. And then we're going to take the square root. 16.76. Let's just say 7.6. Let's just say 16.8. Okay. So there we go there. 116.250. That's the energy that I'm working with now. And I'm going to multiply by 2. Divide by 500. That's the mass of the cart. Then I'm going to take the square root of all that, and it's 21.06. So 21.6. All right, so we've lost, right? We've lost 0.5 of a meter per second. In the end, what are we going to get? So if we notice, without friction, these guys ended up being equal. We know that's not going to happen. The world doesn't work like that. No free lunch. But let's see what the world says about this. 63.5 kilojoules. And we're going to divide by 500. We're going to multiply by 2. And then we're going to take the square root. And that's 15.94. So let's just say 15.9. 15.9. So, good. This is less than this, as it should be. And it's certainly less than this one and this one. So, we have looked at this, and we've done the table. You want to know how to figure out every single bit of that table, and you can create your own. Little roller coaster and make up your own numbers. One other thing that I want to show is these guys right here. Oh boy. These guys, we lost a little bit more here than we lost there. We lost a little bit more here than we lost there, and then we lost the most, I think it was 10,000 here. Okay? So that green is our work due to friction, okay? And that is the energy that got taken away from us. The next thing that we're going to talk about is conservative versus non-conservative forces. And I'm going to set my timer. Set timer for 25 minutes. Okay, so we're not going to talk more about it than 25 minutes worth. So let's come back down here. And erase that a little bit. Okay, we'll just start fresh. We want to talk about conservative, and I don't want to do whatever color that is. I want to do this. Conservative versus non-conservative. Forces. Okay. So let's talk about a couch in a apartment building. Okay, and you live on some floor, and out in the hall there's some stairs that you can go down. And let's see, 1, 2, 3. Let's do one more. Okay, so here's first floor, second floor, third floor, and fourth floor, and fifth floor. So you live on the fifth floor. There's two paths, all right? We've got a window here that will open, and you can slide a couch through it. And there's a pulley system, and you can have a couch that is down here first, and it gets pulled up here, and that height difference is, let's put a number to it, 12 meters. All right. So we've got two paths. We've got one path this way, path 1, and then we've got this path where you go like this, and over here, and up there, and over here. Okay, and then it goes there. All right. Now, let's say that the mass of the couch is 70 kilograms, heavy couch. We know that H is 12 meters. In fact, we know that. I'm writing it to the side, so I'm going to erase that and just put H here. And then we can figure out what is the potential energy of our couch as it's sitting in the apartment. And so what do? We're going to do mgh, and that equals out to be 8,232 joules. Okay. Pardon me. Oh boy. All right. So so here's the thing. We have that much energy. If we were to open the window and push it out the window, and it just went down on its own with gravity doing its thing, then that is how much energy we would get out of the couch. Okay, so let me write path 2 here. Okay. So either way, the gravitational force provides us with that potential energy storage. So we can hoist this couch up. Right, we've got a hoist, and we can pull down here with tension, which pulls up there with tension, and that will allow us to get it up to the top, and then we swing it into the window, and that would be easy. We could do that. That's path 1, or we could do path 2, but a lot of the times people decide which path they're going to take based on the amount of work lost to friction. Which way do you think is going to have more friction? I'm just going to tell you, I think going at path 2, friction is greater than path 1 friction. Because, I mean, you've been there. You've got 2 people, one on each end of the couch. You're both bumping into the walls. You're tripping over the carpet. You're doing all kinds of stuff. It's going to take a lot more work to go path 2 than path 1, where all you have to do is pull on a string, on a rope, get it up there, swing it in. So it seems like a no-brainer. Well, we're now looking at 2 different forces. One force is friction. Okay. The other force is gravity. So gravity allows us to store the potential energy. The friction does not. Once that friction takes energy out of our mechanical system, it goes away, never to return. It's never usable again. So the work of friction energy disappears from our mechanical energy. So lowers our total mechanical energy. Okay, so since we know one stores potential energy and one does not, it just lowers our total mechanical energy, we can say that of the 2 forces, gravity is conservative because it allows us to conserve energy, is a conservative force. Friction is non-conservative. Pretty much the only 2 that we'll see that are conservative, and I've talked about this a little bit before, but we've got springs, which are conservative, and gravity. those are our two. Friction certainly is non-conservative, and you'll find that there may be others as well. But we're just going to specifically talk about friction first, though. Okay, so let's do what they do in a book. Sorry. Let's do what they do in a book. So we have point A. We've got point B. And in between, imagine I'm at the whiteboard and I've drawn this out, this smiley face, and I'm going to go from point A to point B, and I'm going to erase with my eraser straight through from point A to point B. Okay? So that path that I take has so much friction in it. Okay, so the work of friction for path 1 let's do the same thing. We've got A, we've got B, we've got our smiley face, and this time we're gonna do this path. Okay, with my eraser. So I'm gonna erase like this, and then I'll just redraw it. Okay, this path is longer. D2, path 2. D2 is longer, D1 is shorter, so D1 is less than D2. And our work of friction for path 2 is also less. So work of friction for path 1 is less than the work of friction for path 2. Okay, good. So we can see that the two paths are different, and that means that the amount of work due to friction is 0. What am I talking about? The amount of work due to friction is path dependent. Dependent. I don't know. E or A, I can't remember. Okay, path dependent. For gravity, it is not path dependent. So, what does that mean? Conservative forces are path independent. I think it's supposed to be an E. A or E. You guys, you can kill me about that later. Okay, non-conservative are path dependent, or they depend on the path. So, path dependent, path non-dependent are two ways of talking about conservative and non-conservative forces. That is definitely testable stuff. I will be, this will come back, okay? So you need to know this right here. All right. So let's look at gravity and path integrals. Okay. So here we are. We've got our couch. We're going to go up the stairs. Uno, dos, tres, cuatro, cinco. And then throw it out the window. Okay, we can do that. When we do, we're going to go all the way from A back to A. Okay? So we start out here, we go that way, and we're going to do the work from A to B, but that happens to just be, here's point B. That happens to be the, how do I want to do this? A, B is path 1. Oh. Okay, let's do it two different ways. All right. Let's go. This is path 2. This is path 1. Okay. So we were going to go from A to B. Actually, we're not going from A to B. We're going from B to A. And we're allowing gravity to do it. So this is totally our work done by gravity. So work by gravity. And that's the integral of path 1, force of gravity. Oh my gosh. I'm sorry, I'm getting tired, guys. Just hang with me here for a second. Okay, our force of gravity dot dr, okay, for path 1 has to equal path 2. Okay? So if we were to do the work BA, AB, we should get an integral. It's a circular integral of the force of gravity. So we're going like this in a circle. Okay, that circle is this integral. So dr, that means that we're going to go up one side. Oh, that has to be path 2. Okay, so we're going to do the integral over path 2 up one side, fg dot dr, and go back down the other. So the total ends up being the work done by gravity going from A to B ends up being 0. Another way to look at that is that the work of AB is equal minus the work of AB is equal to the work of BA. So that's all I did was I took the one and subtracted the other one from it, and we end up with 0. Okay, so again, path independent. Okay. We're going to do an example in the next video session because I need a break.